Welcome to Wireless Future. I'm Emil Björnsson and I'm here with Eric Larsson. How are you?
Hi Emil, so I'm great. How are you? Good to see you again. It's been some time since we recorded, I think, and it's always good to see you over Zoom in your studio suit.
Yes, so some people haven't noticed that we're actually not in the same room, even if it looks like that in the video version of this podcast. So this is episode 35.
35, wow.
And today you have found a paper that was quite interesting. The Road to 6G, 10 Physical Layer Challenges for Communication Engineers, which is a paper that was, I think, published 2 years ago. And the plan for this episode is to talk about these challenges. What are they all about? And are these still challenges? Where do we stand? And various things around that.
Yeah, they should make for an exciting discussion. So first, thanks for sharing the paper, Emil. Papers with challenges in the title always attract my interest somehow, because as communication engineers, we're continuously looking for things to do and for our grad students to do, obviously. And perhaps this paper it was published like 2 years ago, which makes it even maybe more exciting, because then we could reflect a little bit over whether the challenges described there had already been solved or at least addressed to some extent.
Exactly. And I often get emails from people saying, what research topic shall I look at or spend my time on in my thesis or whatever? And then I usually are directing people to papers like this, where people have spending time on actually elaborating on what are challenges, what are open problems, because that is where you can easily find things to work on as a young researcher. All right, so before we go through these challenges, I think in the first introduction of this paper, they are describing what they think are 3 scientific pillars for the development, and I think the challenges are then categorized based on these type of things as well. So before we just start on going through the challenges, I was planning to read those ones. So the first one is to push the communication to higher frequency bands, such as millimeter wave and terahertz. The second one is creating smart radio environments through reconfigurable surfaces. And the third one is removing the conventional cell structures, such as self-remassive Mimo, distributed Mimo, or whatever we want to call those type of things. And the first of the challenges then is about reconfigurable intelligent surfaces or meta surfaces or whatever we want to call them, and about their implementation. So this is a challenge related to phases and resolutions of the cells, or what is it?
Yeah, so one thing they talk about in the paper is like when you have the atoms in a reflecting intelligent surface, then you'll need to dynamically reconfigure the phase shift of each one. And in a real implementation, as far as I understand, then one might not be able to sweep the phase or adjust the phase over the entire range around the unit circle. So like from 0 to 2 pi, that's one thing. And also one might build the actual electronics from components that rather switch between a pre-configured number of fixed phase positions, so that rather than sweeping continuously from say 0 to 2 pi, you'd adjust in steps, 0, pi, half, pi, 3 pi half, and so forth. And the paper makes a case that, this can of course be done. I mean, quantizing the phase steps roughly, but there's also a performance loss that comes with it. And the numbers were quite staggering if you go to extremes, like the maybe most extreme would be like 1 bit quantization of the phase, and then they lost something like 20 dB in the beam gain, and also got some side lobes. And then the paper looked at like, well, what if we can't adjust the phase from 0 to 2 pi, but maybe only from 0 to pi? And then no surprise, there is also a rather substantial loss. I think there's a figure mentioned 7 dB in that context. So to me, it seems that some fair number of bits will be required here for these surfaces to really be useful, and also one would have to implement the capability to actually adjust the phase over the entire range from 0 to 2 pi, which doesn't come as a complete surprise. I mean, if we think of it in beamforming, it's like, well, we get a coherent gain as long as the beam components are in the right half plane, so that they at least walk in the right direction. But that more or less requires that we can go, at least it requires that we can go more than halfway around the unit circle when we adjust the phase. So to me, rather intuitively reasonable conclusions.
Right. Yeah, I think this research is really starting from people for many years building metasurfaces or similar kind of reflect arrays or things that were fixed, but still having this kind of phenomena where you can phase shift the signals within the individual elements. It's interesting so this is written, this paper, by people at Queen's University in Belfast, and there's a mix of like communication people like us, but also people working with antennas and electromagnetics. And I think that sometimes when you read about the losses from low bit RAS, you hear that it's only a few dB that you will be losing, but apparently when you use real hardware, there are larger losses that can happen.
Indeed, yes, sure. I mean, so there are, of course, a number of friends and also former students, in fact, in the co-author list of the paper here. So one thing that maybe wasn't so obvious is the side lobes aspect. I mean, it isn't entirely clear why side lobes would be a big deal at all with a REES. Do you have any insight into that, Emil?
Right. So I think traditionally people building antennas or radar system or whatever have been very concerned about side lobes. They want to have one clean beam in the right direction and nothing else. And I think in some situation where you try to just detect angles or signals coming from one angle or so, this would make your modeling of potential directions and stuff like that work much more smoothly than if you have very chaotic side lobes.
Yeah, I mean, isn't the point that, I mean, if you're going to use the array for like direction finding, then you you really don't want side lobes. But if you're going to use it for communications, what really matters is the gain in the main beam direction that you're pointing to, whether there are side lobes or grating lobes, or I mean, of course, those correspond to like receiving or transmitting in underside directions, but that might not matter much for the performance of the communication link eventually. What does matter is the gain in the intended beam direction, mainly.
Right, yeah, and if you then aim your beam or your gain towards a certain location and you have users elsewhere that might be interfere with you, then at the end of the day, or at least on the average, it's the total amount of energy that is radiated outside your main beam that matters. But of course, if it's very flat outside the main lobe, then you always get hit by roughly the same interference levels, while if you have big variations, it could be a bit more random, the interference levels throughout your coverage area.
Yes, but even for, say, a standard Mimo array, I think this is a bit of a misconception that grating lobes would be a problem, because if you think of it, if you have a uniform linear array with half wavelength spacing, then as we know, we can form a beam, and the beam is going to have a main lobe and it will have some side lobes that diminish in magnitude. Now, if we change the array topology and aperture, let's say that we stretch out the spacing between the antennas, then what happens is that the main lobe becomes narrower. The gain in the main lobe direction is unchanged, but we will see also grating lobes appear in other directions, but the total amount of interference that's spread around is still the same. I mean, the main lobe becomes narrower, but the price to pay for that is that we get the grating lobes. So what used to be interference directed in directions very adjacent to the main direction of the main lobe now ends up in the grating lobes, which is not necessarily a problem, I mean, in Mimo or even multi-user Mimo communications. So I think that's an important point to drive home, that grating lobes or side lobes much of the time don't mean or aren't necessarily bad, unless the array is to be used for angle of arrival finding or positioning. Then that could be a different matter.
Right. Yeah, and going back now to the RAS and their phase resolution, for example, I have at least seen papers with people making prototypes from recent years with 1 bit, 2 bits, and 3 bit at least. Maybe there are a larger number of bits. So with 3 bits, you have 8 different phase values, and hopefully they are uniformly spaced between 0 and 2 pi. And in those cases, yeah, you can phase align things rather well by shifting the reflected signals.
Yeah. So, what are the other challenges in building a RES, Emil? I think the paper talks about reconfigurability dynamically. Is that something you could speak to and maybe relate what the authors here also have to say?
Right. So, as I was alluding to earlier, this is building on the field where people were able to build fixed meta surfaces for a long time, and nowadays we would like them to be dynamically changing, and we really want them to change in real time, so we can serve views that are moving around, for example. So then, yeah, each of these unit cells or elements, or what we call them in these reflecting surfaces, we need to control them, which you can use with some diode, for example. They can switch between different states. And yeah, I think the paper is talking about different ways of building that. And I think in recent years, there are prototypes that are published, and I saw one of them myself at the University of Surrey last year, for example. What I find mostly a challenge is not to reconfigure it, but to know how to reconfigure it.
Yes. So really to estimating the channel impulse responses between each one of the atoms and either the access point or base station or the user terminal, I suppose. So how would that happen in practice? I mean, what is state of the art there really? Obviously one could sound a channel with enough pilots and enough available dimensions. That would be straightforward, but I suppose the difficulty here is that in an environment with mobility, then you can't afford enough orthogonal sequences to sound the channel completely. So some assumptions need to be made either on sparsity or on covariance or on something else.
Exactly. So in a setup with only one antenna at the transmitter and one at the receiver, about 100 or so elements in this surface, well, then there are 100 different dimensions that you can fine tune, and then you typically need to send 100 different or you can repeat the same known signal 100 times, but configure the surface in different ways so that you can observe all dimensions. But as you were saying, if you have ability, that will require a lot of pilot resources to do that compared to how quickly the channel is changing. And I think that what we have seen in the last few years is a lot of estimation papers first, where they just did this without really commenting on the amount of resource you need to spend. And some of them are even considering some kind of on-off configuration, which I think is a bit of a misconception, because on-off in the sense that the RES is turned on and off, or each individual atom is turned on and off, or exactly.
What does that really mean?
So they have the idea that each individual atom can be both change its phase and it can be turned off. So it just disappears from your system. And I think this is a bit of the misconception that usually a diode have two states, on and off. And those are represented by two different phase shifts, but both of them are reflecting the signal.
Yes, of course. I mean, even an atom that's turned off will scatter the wave, right? So in a way, that's not totally an accurate notion, I feel, with this on and off. But okay, sorry, go on.
Yeah, I guess you could build something where you connect every element to, you can terminate it and turn it into something that absorbs more or less everything or something, but it sounds very challenging.
Yeah.
Right, but I think that what I've come to understand is that, yes, sparsity or specific propagation environment is where these surfaces are shining the most, and and possibly the most important use case is when the channel from the transmitter to the surface and from the surface to the receiver are both of them line of sight dominant. So the signal comes mainly from one angular direction, should leave in another angular direction. If you have the same configuration, all the elements, the reflection will be like Snell's law. But then by figuring out how you would like to change it, well, then you change the phase shifts over the surface to do this. And
But that makes sense. I mean, so if you have a rank 1 channel from your base station to the RES and the rank 1 channel from the RES to your user terminal, then fewer pilot resources would be required, obviously, to estimate the channels. Besides, if you're on line of sight, maybe the RES is even like stationary, mounted somewhere, and that means the channel will change very slowly over time, so you could take your time to configure it,
right.
or at least take your time to estimate that part of the channel.
Yeah, you might know geometrically the channel from the base station to the RISC, because both of them are fixed, but not to the user. So we wrote a paper last year where we used some classical array signal processing methods to try to figure out what is the angle to the user using these kind of methods. And the problem, of course, when you send fewer pilots than you have RAS elements, is that there is always going to be some kind of ambiguity. Maybe there is a direction that looks very similar to you to the right one due to side lobes or other things like that. So in order to make it work with high confidence without using so many pilots, we sort of had to first try out a few configurations, and then we look in the direction that seems to be the promising ones and try out new configurations based on those ones until we narrow down the ambiguity to just having one direction that works well.
Yeah, that sounds like a clever approach. But I mean, fundamentally, it seems to me there is not much of a difference in estimating a, say, base station to RES channel compared to estimating a base station to user channel in conventional Mimo in either case. I mean, the difficulty with the RES is that you have more coefficients to estimate, so you need either a larger dimensional space that can fit the pilots, or you need to rely more heavily on structure of your propagation environment.
Right.
Yes.
Yes. So I guess it's particularly similar to some kind of analog beamforming situations where you, at the base station, where you the signal reaches all of the antenna elements, but we cannot extract them there separately, but only the sum of them, as we would have in analog beamforming. It's the same thing where you always need to reflect the signal elsewhere to observe it.
Yes.
All right, maybe we should move on to the next challenge. And the paper is now going into this cell-free or distributed Mimo scenarios where you have access points spread out over the city or so and serve users without sort of dividing them into cells. And the paper talked about network-centric and user-centric and challenges related to that. So Can you say something about that?
Oh, yeah. So I think there's this notion of user-centric networks where the idea is that, to my understanding, we have like a distributed Mimo or cell-free Mimo system with lots of antennas spread out, right? And they are somehow capable of operating together phase coherently. And then the idea with user-centric is that only antennas or access points that are close, I suppose in a path gain sense, to the user would actually contribute towards serving that user. To me, that seems to be just the natural outcome of any reasonable downlink power control scheme in a, say, full-blown cell-free massive MIMO approach. In other words, if you just treat this whole network as a bunch of access points, potentially a very large bunch of access points, they could cooperate phase coherently, and then you work out for every user in the system what are the optimal power control coefficients on downlink. So how much of power should each respective access point each access point spend on that respective user, then you'll find that, well, only the closest handful or so actually spend a significant amount of power and the rest spend very little. And if you just truncate them and say that, okay, only the 5 closest are to contribute, then we have the user-centric approach, which obviously makes a great deal of sense from every perspective.
Right.
Then in reality, I think things aren't fully as simple, because at some point there will be a scalability problem, in the sense that now if we just grow and grow and grow the network, somehow all these access points will have to be connected somewhere if they are to cooperate phase coherently together. And the only practical way of doing that, as it seems to me, is to cluster them together into groups, right? So you get like some geographical area that has a bunch of access points connected to one processing unit, another geographical area has a bunch of access points connected to another processing unit, and so on. And then in a way, this becomes a little bit like a cellular system where these clusters now are cells, right? And you'll get border between the clusters where it isn't so obvious how to actually handle. I mean, if the clusters can't cooperate phase coherently, then how do you handle interference at the border between the clusters? Conceivably, in practice, the clusters could be made very large in terms of absolute geographical area. And then, as we know, well, if we, let's say, double the size of the cluster, then the area will quadruple, because area scales quadratically with distance, whereas the border area scales proportional only to the circumference, which scales linearly. So the larger we make these clusters, the less of a problem with this inter-cluster boundary interference problem be. But it doesn't fundamentally go away, and this is an insight that seems missing from pretty much every paper that's been written on cell-free and user-centric massive MIMO. And there's no obvious solution to it. I mean, you can't solve a global optimization problem locally somehow. It's mathematically impossible, right? I mean, you might find decent approximations, but you can't solve it to optimality. So
right.
I think it does remain a challenge a bit here, what the authors describe in the paper, in fact. And I know, Emil, you have worked extensively on power control and signal processing in general, but power control in particular for user-centric MIMO networks.
Yeah, and I think if you, like me, like to formulate optimization problems that you can solve, then as you were saying, the problem is that there is no feasible formulation, perhaps, where you have where you can solve a global problem, because you're not supposed to do it globally.
No.
But I guess one of the things that we are doing now with the network deployments is to actually connect base stations to cloud computers at the edge that might be taking care of all the base stations in a few kilometer radius, for example. Could these cloud computers also be connected to each other so that they could pass around some signals to address this interference at the edges?
I think they could. I mean, but aren't you just moving the problem up to a higher level? I mean, say you connect these clusters, groups of them in 10 or 20 or something, then you get like super clusters consisting of 10, 20 clusters each, and then maybe you can cooperate phase coherently within a cluster. Let's say that's possible. Then you would at some point get like boundaries between superclusters, right, where you'll have interference problems because the superclusters can't cooperate phase coherently. But again, the scaling is favorable here. So if you double the diameter of such a supercluster, then its area will quadruple, but the circumference will only double. So the geographical area where you have an uncontrolled or an interference problem that you can't easily control will, in relative terms, diminish. But fundamentally, it is like solving a global optimization or distributed global optimization problem through local computations, which in general isn't possible.
Right. Yeah. So even if you can sort of ensure that every user can be served in some sense by all of its nearby access point, maybe belonging to two different cloud computers. Even if they exchange information, you can't solve these global problems. You can just resolve some of the interference issues maybe at the local level.
Yeah, it seems to me, at least it's an open, to my knowledge, open question how to actually do it. But when the clusters become large enough, I mean, the number of positions, geographical positions where you get really unlucky will be relatively fewer if you're right in the middle of like two mega cluster networks and they can't cooperate phase coherently. There might be an interference issue, but that on the other hand maybe could be resolved through other means, some dedicated spectrum to, I don't know, offload those and suffer there.
Right. Yeah, at least there seems to be a lot of interesting research going on in this area right now. Some of it connected to people working with Cloud RAN and Open RAN. So I think that is a place to look for people who want to contribute in this field.
Oh, absolutely. Yeah.
All right, the next challenge.
Yeah, I think one is power control that we talked about already,
right?
Which is essentially an optimization problem, at least in its canonical form. For the communication engineer, power control becomes an optimization problem that you can, in some, say, simplified circumstances, solve to global optimality if you have all information in a central place and a powerful enough machine there.
Right.
But in practice, I guess you'll apply rather heuristic and simple algorithms that can be run and distributed throughout. I think, Emil, you had worked on power control. Both of us actually worked on power control. I think we worked more recently on it.
Yeah, this is one of the things I've been working on recently and try to understand this, because if you just consider classical power control in a single cell that is separated from other cells thanks to frequency division or something, then it's all about, okay, you have multiple users in your cell. Some of them are near and some are far, and those that are far, their uplink signal will be much weaker if they transmit with same power, so you let the user that is nearby cut down a little bit of this power, and in that way you are balancing between them. You get some variation in the power, but you can handle it in your hardware. But then when you put this into a cell-free system, then you have this user that is near and far to one access point. Mm-hmm. Then you put that another access point that had the opposite situation to them because it's on far away. Then you, in the uplink, then who should transfer with high power or not? Mm-hmm. And
so I think that's a good example that really captures the fundamental difficulty of power control in cell-free MIMO, right? Of course, you also have the phase angles to play with, so you can beamform, but from a power control perspective, it's really exactly what you just said.
And I think in the uplink, what I have seen in my work is that even if it's hard to solve this in an optimal manner, if you let people do some simple, follow some simple policies like transmit with rather high power unless they create a lot of trouble, then you can deal with a lot of things using your beamforming at the receiving access points. So you can resolve some interference with that. The downlink is much more complicated, I would say, because you would like to sort of provide users with somehow similar performance. So how would you do that? Well, one idea would be that if you look at the users that you are serving as an access point, then you look at how strong their channels are, and you say, okay, let's transmit with high power to those that are far away and low power to those that are nearby. And that turns out to be a really bad policy because you are sort of screaming to reach the one that is far away, and you get a lot of interference to those that are nearby. So it's more like the opposite you want to do. You would like to sort of opportunistically transmit a lot of power to nearby users and less power to those are far away, but then those far away might not get any power at all, and then it all starts to connect and becomes hard.
Yeah, so I think this one remains a challenge, right? I mean, as stated in the paper. So what other challenges do we have in user-centric and cell-free Mimo implementations.
Right, so the signal processing needs to be
signal processing, of
somehow.
course, and especially handling the sheer amount of data that we get, right, and baseband data, like where to bring all this data, and devising processing schemes that scale favorably when the network size is increased. That I feel a lot of progress has been made. I mean, we have papers together, Emil, for example, where we show that on uplink, of course, one possibility is to bring all the baseband data to a central unit and then run maximum likelihood detection or MMSE filtering or anything favorite method you want. But we gave a paper once with one of my students where we showed that. Let's see. So my student showing the paper was that we could distribute the processing such that the front-haul load becomes independent of the number of access points, even if the access points are connected like in a daisy chain or stripe topology. And the trick here was that every access point should compute a sufficient statistic, which essentially is to take the incoming data and perform a spatial matched filtering of that, and then forward that on the front haul, and every access point receives from its upstream from the access point next in line, receives its sufficient statistics, and then it adds its own and forwards to the next. It becomes sort of like an accumulate and forward operation that's performed per access point. And it turns out that whatever is received at the central unit is a sufficient statistic for detection. There's also a channel Gramian required that needs to be accumulated in the same way. But bottom line is that the front haul load on any segment on the front haul becomes independent of the number of access points. So that's a quite important insight, in fact. And on downlink, similar things can be done. I mean, the Gramian needs to be obtained centrally, and that could be done through an accumulate and forward type of process that I just suggested. And then on the reverse, the central unit would pre-process the data using this Gramian, and each access point would perform a spatial matched filtering before transmission. But there are also more sophisticated techniques. I think you have some papers you co-authored, Emil, on team pre-coding for
right.
the downlink that maybe are too complicated to explain in detail on a podcast, but you could give it a try if you like.
Yeah, I think the principle is not that hard. So the nice thing with the uplink is that the method that you describe is essentially a way of doing a sequential estimation of something, where you estimate it and then you feed in with new information that the next access point have. And in that way, you don't need to know exactly everything that the previous access point knew. You just need to know their estimate and their essentially the accuracy of their estimate.
I think there are two ways you can think of it. You can think of it as a sequential. I mean, if in the MMSE decoding framework, you can think of it as a sequential MMSE or Kalman filter. In the maximum likelihood decoding framework, you can think of it as a consequence that the sufficient statistic for decoding is a linear combination of quantities that are computed per access point, so therefore is accumulate and sum will function. Right. But okay, sorry, there's a...
Yeah, but if you think about the downlink now, it becomes more challenging. So say that you have 10 access points, they are along a cable, and they get the data from the from the central processing unit to the first access point, which feeds it to the next one, and so on. And they now need to make decision on what to transmit. So the first one doesn't really know anything apart from its own channel knowledge and the data, so it needs to make a decision on how to transmit. Then it can tell the next access point something about what it decided, and then the next one can then take its decision on how to improve the transmission based on the knowledge of what had already been decided, and to use its own local information to try to improve things. And then it goes on like that, and in the end, the last one can do the final refinements. But since you never go back and update things, the problem then is that the first ones needs to make decisions that are suboptimal because you don't have full information. But so we're saying there is something called team decision theory that can be based on how you can use statistical knowledge about what the others are going to do, or use their, that they exist, and you know that you are having a common goal but incomplete information, and you can use this when things to devise methods that are optimal in some kind of team manner. And they become challenging when you go into the details, but they work surprisingly well, I would say.
Yeah, I feel like they merit an entire lecture or podcast on their own to explain in detail, but maybe the take home for the broader audience here is that signal processing in distributed Mimo, user-centric and cell-free Mimo scales actually rather favorably, although it might not seem so at the surface, but much of the actual signal processing computations can be distributed and implemented at the individual access points without loss of optimality with respect to a fully centralized implementation.
All right.
Great, Emil. So where do we go from here?
Yeah, I think we are supposed to switch topic towards
I think that's what we said that we would do. Yes, so we got one more, I think, to talk about, that the paper also has as one of its main themes, and that is the perceived shift to higher frequency bands for 6G and maybe beyond. So higher frequency bands here, I suppose, means beyond millimeter wave, and so up to the terahertz band.
Yeah, or just improving and using more of the millimeter waves. I guess so far there are some deployments in around 28 gigahertz, but you can do things in 50, 60, 70, 80 gigahertz as well.
Yeah, I mean, there seems to be almost an infinite spectrum available up there. Of course, the challenges also scale somehow with the carrier frequency, right? Because of Doppler, channel coherence time and path loss and phase noise perhaps in the circuits. So now what are the main or most important challenges for us to work on here, maybe going from the paper that we read?
Yeah, so the paper is first describing 3 different challenges or categories that are related to hardware implementation and verification, I would say. So the first one is how you package and interconnect a transceiver. So if you're not into building actual radio electronics, you might think, let's just take something that was designed for 3 gigahertz, and then you go up to 30 gigahertz, and then the wavelength is cut by factor 10, so then you shrink everything down by factor 10. But then it doesn't work at all like that. But the thing that is scaling a bit like that is the antenna elements. So if you want to have a certain gain of your antenna, well, then it becomes smaller and smaller as you go up in frequency. And then this is also one of the main causes for the worst path loss that people are talking about, that the fact that you have a smaller antenna at the receiver side.
Technically it's not the path loss, it's the effective area of the antenna that shrinks, right?
So if you now have a given number of antennas and you want to still maintain them with half wavelength spacing or some other fixed spacing, then the spacing between antennas also becomes physically smaller, and now these elements are going to be connected with other components. So after the antenna there will be a small wire or something that connects it to different converters and low noise amplifiers or power amplifiers in the downlink, and there are converters and filters and things like this, and all these things need to be shrinked into a smaller size. And you need to package the whole thing, and when there is a smaller size there might be new physical phenomena that are appearing. You might have higher losses of the signals that goes through a piece of metal, and they might be coupling with each other. And yeah, just squeezing everything into the same package is really challenging.
Yeah, indeed. I mean, so I find it just amazing that it's possible to build these components and make them work. And somehow I feel like those building the microelectronics here are the real heroes. Now, notwithstanding that, of course, there are also challenges for communications theory engineers like ourselves. And maybe one of them is just to realize that not only propagation changes when we go up to very high frequencies, but also the behavior of hardware circuits. And there are all sorts of issues here with nonlinearities and distortion and phase noise and out-of-band leakage and you name it, that we can't ignore. And in fact, that should be at the heart of any design on, say, the communication physical layer, be it waveforms or signal processing algorithms or anything that goes in there.
Right. So a lot of things becomes harder, and as you were saying before about phase noise and more generally, I would say a lot of things, imperfections that you have becomes much worse when the wavelength shrinks, because then they have a proportionally larger impact on your the cleanness of the signals that you can generate and receive.
On the other hand, you have more bandwidth to even waste, right? I mean, out-of-band radiation, which is a huge deal at sub 10 gigahertz frequencies, might not matter at all at terahertz, because to start with, I mean, the out-of-band radiation doesn't reach very far. and also you have so much spectrum that you don't really care. You can put some extra guard bands in between, and that solves the issue. So, but I think we got to be acutely aware of those aspects and the new questions and issues that appear when we move up so high in frequency. And as you suggested, I mean, the hardware behavior becomes maybe qualitatively not so different, but quantitatively in many ways totally different.
Right. Yeah, and just squeezing everything into an area that is, all radio electronics in an area that is comparable to the size of your antenna array becomes really challenging.
So small, yeah.
Yeah, and in addition then to this packaging and interconnect between the different components, the next challenge that they're describing is transceiver design, which is of course closely related. And I think here I would like to bring up this kind of thing when it comes to hybrid beamforming or other kinds of ways of implementing things, because as we were saying, the antenna elements with the fixed gain shrinks. So we typically want to have more of them so that we are filling up roughly the same area as before. So then you get more elements. And then there's of course two benefits of that in general. One is, yes, you get a better gain thanks to many antennas. And then the second thing is that we are able to also transmit and receive multiple data streams in different spatial directions. And it might be that as we go up in frequency that these things are decoupling more and more, so that we have a beamforming gain that is also always proportional to the number of elements, while the number of streams might then start, that the channel around us is supporting might become a smaller and smaller fraction of the number of antennas.
Mm-hmm. Yeah, weird emphasis on fraction, right? Because I think you might be right that the higher we go in frequency, the more of like line of sight like environment we are going to see. Maybe there'll be some specular reflections, but just a few of them, and just adding more and more antennas will not resolve perhaps many more reflecting or scattering centra. So there are like some interesting trade-offs there, yes.
Yeah, one cluster can potentially be divided into multiple resolvable clusters potentially, but
potentially.
But I think this then opens up the question whether it is worth building transceivers, even if we potentially can it, which have a full resolution in terms of that every antenna element is connected. And I think already now these 5G base stations, even in the 3 GHz band, they have more elements vertically than they have transceiver chains vertically. Then as a communication engineer, you need to also be aware of what is really a transceiver chain. Because I used to think, you have an antenna and you have some box that we call a transceiver chain, and then we have the digital transmissions. But if you look into that one, it's actually much more complicated, because sometimes you hear, if you do, for example, the analog beamforming or hybrid beamforming, you need to have fewer transceiver chains. But it doesn't really work exactly like that, because if you have a multitude of antenna elements connected to the same signal from the baseband, then you still need to have some components that are per antenna. So you take your signal and then you put your phase shifters, for example, or it might be a traditional phase shift and it might be something more metasurface like, and after that you would like to put your power amplifiers. Because if you do it before the phase shifters, you lose a lot of power, because the phase shifters are sort of losing a proportion of the power. So you prefer to put them afterwards. And then you might have filters and things like that put at different places as well. So even when you are connecting multiple antenna elements to the same baseband signal, there are some components that scale with the number of elements as well. So there's a lot of design aspects here that needs to be considered, I think.
Yeah, that's a good point. I mean, and I think it's important for folks working in Mimo and communications engineering to really take the red pill and open the box and realize what all the components that go inside of that, right? I mean, taking the blue pill would be to just pretend that y is equal to hx plus noise and then keep going, but in reality things are very much more complicated.
Exactly. So we might come to a situation where we could build things that are fully digital and perfect, but we don't want to do it for sustainability or cost or whatever reasons, and then we or maybe it's just too hard to build it, to squeeze it into a small device. Right. There is one more challenge that they are describing called measurements and standardizations. And this is something that I feel when I've tried to expand my own research. I would say that it would be nice to not only work with math and algorithms, but also do experimental works. But then you also see how it becomes increasingly more complicated, because, if you will do new experimental work, you should probably be at these higher frequencies to motivate that you are doing things that people haven't been doing before, and then you need more and more equipment. Of course, before all of these transceivers have been designed for commercial, you need to buy the big signal generators and the big equipment that are brute force able to do everything you like to do. So I think carrying out measurements just becomes more and more challenging and costs more.
Indeed.
And one of the potential solutions that I see there, or a way around it, is at least that thanks to better computing power, the ray tracing or electromagnetic solvers becomes more and more capable of predicting things. So I think this is where a lot of the design of things is happening today as well. That people are designing very complicated transceivers in software, and then they simulate it using more and more refined software to predict the behaviors, and then you come to the point where you actually try it out in practice.
Yeah, it's good to know. So I have less intuition, I think, for how accurately one can model real propagation using these tools, but that's good to know.
Yeah, and I think during the last 12 months or so, I've been receiving demos of 3 different companies' software for both propagation modeling, and they have aspects to describe different hardware capabilities that are related to Mimo, or now they try to add RAS features as well. So I think there are certainly developments there, and and using GPUs to power those algorithms for the ray tracing or electromagnetic solvers is another good aspect, I think, that makes it more tractable. All right, there are two more challenges in the paper, and the first is about signal processing. Channel estimation in particular, I think.
Channel estimation. It is an important one, obviously. Getting channel state information especially at the transmitter. At the receiver is also important, but somehow we can always make it even without, right, through different blind decoding algorithms and so forth. But getting channel state information at the transmitter is absolutely crucial to make any form of MIMO system, or REIS for that matter, to work, because if you don't have it, you can't direct power in the appropriate direction in space.
Does this apply both to single-user and multi-user MIMO?
Oh, I think so. Don't you agree? I mean, for single-user, you need to know, like, the channel response. You can perform some form of beam steering, maximum ratio transmission, or something of that sort. For multi-user, it might be even more critical, especially if you are to apply like any sort of interference suppression scheme, like zero forcing transmission, for example, where you direct power to one user, simultaneously place a null in the direction where the other user is located, and vice versa. So it is critical. It may be even more critical in multi-user MIMO than single-user MIMO, but...
Right, I was thinking that in the single user case, you since all of the data streams are meant for the same receiver, you could take care of some of the interference issues there.
Well, fair enough. I mean, or I agree, for single user MIMO, then interference isn't an issue. I mean, it could be an issue between different cells and all of that, but within, say, within a cell, interference is an issue. The issue is just to get the array gain so that as much as possible the power ends up at the spot where the user terminal is actually located. So now, channel estimation in principle is a rather simple business. If you have enough resources to assign orthogonal pilots, then you just have your users transmit pilots, and if they are orthogonal to other signals or pilots or anything else transmitted simultaneously on uplink, then these pilots will be received interference free, and you can estimate the channels to any precision you like, more or less. The difficulty is when the dimensionality of the coherence block doesn't allow for enough orthogonal pilots, or for long enough pilots to get the integration gain that gives sufficient SNR of the channel estimates. And this one, I think, is a highly important challenge that's largely unsolved, because what happens at the higher carrier frequencies is that the coherence block shrinks, so there's less room for pilot sequences. So the pilots will have to be shorter, and one might not be able to afford assigning different users orthogonal sequences and so forth. And then the only way, I mean, we're back a little bit to where we started with the REIS, right? We don't have enough resources for orthogonal pilots. Then what to do? Well, the only thing to do is that we have to rely on some prior knowledge on the channel, either like knowing that it's correlated with some specific covariance matrix, or that it's sparse in some domain, or that we have prior information of some other sort. So I think here the paper is spot on this one, and estimating channels still remains a major issue for especially high carrier frequencies and high mobility environments.
Right, and I think you and me have been working a lot on reciprocity-based beamforming under the assumption that the user device only have one antenna.
Oh, yeah.
Because then you can just send an uplink signal and you get everything from just one. But then, as you add more and more antennas into the user device because of the higher frequency.
So now you have a whole array at the user. I mean, each antenna be assigned its own orthogonal pilot sequence? Maybe there just isn't enough room for that. And And also on the algorithm side, I mean, I think you, Emil, have worked a lot on channel estimation algorithms that work under the assumption of a correlated Rayleigh fading channel, so that you know they have Rayleigh fading, you know the covariance matrix of the spatial covariance of the fading, and of course if you have that knowledge, you can greatly improve the quality of the channel estimates. But the problem is that, well, fading isn't a stationary process, right? I mean, if you have an antenna and then you move around a little bit like this in a small wavelength sized area, you'll see something that looks fairly stationary. Maybe it makes sense. You can talk about covariance matrix or the fading, but once this antenna drops behind a corner or something here, then a new multipath strong component will appear, and this covariance will just change abruptly. And then if you don't track that change in covariance, you could get grossly inaccurate estimates. So that's another difficulty here that has not been very well solved, I think.
Yeah, I think that when we in academia design algorithms and assumes some kind of stationarity in the statistics and the existence of covariance matrices, I'm not sure to what extent it actually have been proved or demonstrated in measurements that there actually exist covariance matrices that are stationary, and of course there should exist something like that. Yeah. But
over a short enough time scale, there will. I mean,
short enough time scale or small enough physical area. Will that physical area be large enough so that you can get the richness of the Rayleigh fading distribution? I don't know. I still haven't seen this kind of.
So that's an
things.
Open question, I think. So here, I think the paper now here, I think the authors are spot on this one with channel estimation in short coherence intervals, high mobility, high carrier frequencies, potentially many antennas at the user terminal.
Right, and I think they mentioned when it comes to covariance matrices that maybe one can use random matrix theory methods to deal with statistic. I mean, if you estimate the big covariance matrix, you need to have at least as many observations as there are dimensions just to get something that is not rank deficient.
Yes,
but you need many more than that in order for the eigenspaces to be good. And I've looked a bit on that in the past, and I'm not really convinced that random matrix theory helps us.
It sounds good, but I'm also not really convinced. And I feel like, well, this might be a potentially good use case for machine learning algorithms that could, like, over time learn what the environment looks like and maybe have access to some side information in terms of geographical location of the user terminal. But it's largely an open problem, I think we can say.
Yeah, I think it's more like, okay, we will have incomplete information. What can we do with that information that we're having? Because it might be hard to fill in with something else that we didn't observe. But yeah, maybe machine learning can do it in certain situations.
Maybe, yeah.
I think the last challenge that they're describing is a variation on this theme. I would say that suppose you can learn your own channel well, but there is interference, and then typically your receivers or transmitters would like to know the covariance matrix of that interference, so you can use it to design some
But that can, of course, be estimated, right? I mean, just you stay silent or you subtract your own channel estimate, so you get only interference and noise left, and then you can estimate the properties of that interference and model those accordingly, maybe through some, I mean, in the simplest case, through a correlated Gaussian process that you plug into your likelihood function when you detect your data and so forth.
Yeah, I'm not sure if that is the biggest challenge compared to all the others we have been talking about, because typically when you like to do some kind of regularized zero forcing, the matrix that you invert to figure out where to transmit is essentially the sample covariance matrix of what your data transmission. It's an approximation of that one. So I think those type of things have been used for a long time by the industry. Even if it doesn't help give you nice mathematical analysis, it works.
Yes, it does. Yeah, and of course there's also the related issue of going beyond Gaussian distributions to model interference. Some interference out there has a heavy-tailed distribution, which means that with some probability you get an outlier sample. And typically receivers that are designed for Gaussian noise perform rather poorly if they are subject to noise with outliers. So that's another little niche where there is good opportunity to make contributions.
Yeah. And I think in general, when it comes to some of these estimation methods, that temporal correlation can be helpful, at least to some extent, that you for extended amounts of time will see the same scattering cluster. So there is some kind of statistics there, but then, all of a sudden you move around the corner, then it doesn't work anymore.
No, absolutely. I mean, temporal correlation is just another way of saying that the coherence time is longer, more or less, right? If you can like extrapolate or interpolate or...
All right, so I think we have gone through all of these 10 physical layer challenges for communication engineers. So
I think we did, indeed. So
are they still open challenges?
Yeah, I mean, at least some of them. I mean, as we said at the outset, the paper here that we started off from as inspiration for this discussion was published like 2 years ago. So probably it was written like almost 3 years ago. And some of these challenges remain open, definitely. I mean, I think we touched upon especially signal processing aspects and of course, those problems relating to the microelectronics implementation. So much of what's being said here in the paper does remain relevant to this day and is likely to remain relevant for the foreseeable future.
Yeah, and I think in some of these challenging areas, there have been quite some algorithmic development in recent years related to some of attempts to deal with some of the scalability or different heuristic algorithms for power control or different estimation methods and things that. But I don't think we still have a confidence enough to say that these problems have been addressed.
No, as you said, I mean, there are lots of papers and algorithms, but most, or if not all of them, are of rather heuristic nature. And I think it still remains to settle rigorously on a theoretical framework here for many of the questions that we discussed. So absolutely, there is work still left to do.
Great. And I hope that our listeners will be interested in learning more about these topics and take part of the future development of 6G and the research into resolving these challenges. So we put this paper in the description of this episode and also a few other papers that we have been mentioning along the way that might be of interest to you to read. And with that, I think we are done for today.
I think we are. So then, thanks, Emil. Take care.
Thank you all for listening. Bye-bye.